Welcome back, everybody. We continue with the mini course on nonlinear Grassmannians and Zag manifolds. First part of this course will be presented by Cornelia Vizman, my advisor, from the West University of Timișoara in Romania. The stage is yours.
Thank you, Joanna. And I have to thank the organizer for giving me the opportunity to give a mini course, which is something very special for me. I don't think I've done it only once, but long ago, and to a much smaller audience than this one. Together with Stefan Harald, we decided to talk about nonlinear Grassmannians and flag manifolds. We have several joint papers on these spaces, these mathematical objects where I want to introduce. There is also some joint work with François Balmaz on the same subject. Stefan was said we should explain why these spaces are important. Of course, they appear in as shape spaces. This nonlinear Grassmannian, this space of submanifolds, for instance, curves in the plane, and also the flag manifolds, which are like, for instance, curves on surfaces in the space. So it's a nested set of submanifolds of a given manifold, which with Barbara we hope to use to make it useful in the shape analysis. But our interest in nonlinear Grassmannian and nonlinear flag manifolds comes from conjoint orbits. Conjoint orbits of diffeomorphism groups. This was already the theme of my PhD here in Vienna with Professor Timișoara, and so I'm still working on it. So the plan of my talk, so they are conjoint orbits of diffeomorphism groups, in principle the Hamiltonian group or the group of volume preserving diffeomorphisms. So the plan of my first lecture, or maybe first and second, we will see how fast we go, is to present the Fréchet structure of the group of diffeomorphisms of a manifold, if it's non-compact with a compactly supported diffeomorphism, and the space of embeddings. So here S will be a closed manifold, not necessarily connected. And then we pass to the, so this can be seen as non-parametrized, as parametrized submanifolds, and then we pass to, by dividing diff S, the reparametrization group, we pass to the manifold of submanifolds, non-parametrized, and then we have a natural diff M action, and then we can write the nonlinear Grassmannian as a homogeneous space of diff M. And then we can give decorations to the Grassmannians. For instance, we can decorate them with a function, with a form, a differential form, in particular with a weight. So this will be the part that introduces the manifold structure of the spaces and spaces themselves. And then we pass to applications. So first I will speak in general about the mutually completely orthogonal actions in dual pairs. In particular, applied to the ideal fluid dual pair due to Marcel and Weinstein. Then doing reduction on one leg, one gets conjoint orbits on the other leg, and in this way we will get conjoint orbits of the Hamiltonian group. Those of the group of volume preserving diffeomorphisms are not obtained from a dual pair, but we will obtain them directly by Hamiltonian action of the group with volume on some non-decorated or decorated Grassmannians. So, our original plan is that lecture 2 and 3. Lecture 2 will be about the compact group, and lecture 3 about the nonlinear fragment manifolds is prepared by Stefan, and then the fourth one would be like, but we might like the diff vol also, but we might have to interchange things. We'll have we need what is called local addition. So I don't write again. We need something like a local addition for constructing the chart. It is a map, we call it alpha, from the tangent bundle of M to M, such that alpha of 0x for the 0 vector, and the projection of the tangent bundle together with alpha gives us a diffeomorphism onto a tubular neighborhood of the diagonal in M cross M. So this is diffeomorphic onto tubular neighborhood delta M. This is delta M here, recognizable. Yes. You recognize here features of the exponential map. Actually, one could use in the exponential map, but then it won't be defined on the whole tangent bundle. We can adjust it with the fibered diffeomorphism to make it defined on Pn. And with this, I would make a picture. Maybe when M is the sphere, and so here is the tangent bundle, and a tangent vector x, and then we go, if alpha is just exponential map, then we go on the unique geodesic defined by xx till time 1, and so this is a point y, which will be near x, so because we are in a tubular neighborhood of the diagonal delta m. And now x going to y will give a diffeomorphism, and this gives the chart on diff m. We have chart of diff m centered at the identity on M, the identity element of the diffeomorphism group. So we take a vector field and we take it to be small. Actually, since we have alpha, it doesn't even have to be small. we assign the diffeomorphism F obtained by composing alpha with X. And this is a chart. So X goes into Y, as in the picture. And the other charts are obtained by, can be obtained by translation, for instance, left translations by elements of diff M. And if M is not compact, then we use compactly supported diffeomorphism or compactly supported vector fields on M. And we have seen in Christian's lecture that the bracket is minus the usual, the real algebra is the real algebra of vector fields, but the used bracket is minus the usual bracket of vector fields. We will put like this, and the real algebra. So this is the associated real algebra. And we also have an exponential map, which is not nice because it's not locally injected, not locally surjective, but it exists and it is given by, because the flow of X to time t is a one parameter subgroup, exponential X is the time one flow along the vector field X. So I remember Barbara, she presented at the Young Researchers Workshop that X is not locally injected. You can look at the video for S1. You can look at the recording of Barbara's lectures. So what it would be a chart for the embeddings? And I'm writing big enough, or maybe too big. I will have to erase often. Don't know if I can do it as professionally as. Just one. No. So for the space of embeddings, so chart for LSM. So these are the space of embeddings from S to M, and as I said, S is closed, possibly not connected. So chart at 5. So it is modeled on vector fields on M along phi. So it's a Frechet space. So we will get again a Frechet manifold, like for the diffeomorphism group. It's actually, if S is M, we get the diffeomorphism group. So this is S, and here is our heart. Not symmetrical. Then we have a vector field y phi along phi. So here at phi of s, it is y phi of s, a tangent vector, arbitrary in M, and then we apply our alpha. So this is the image N, and we apply our alpha, and so we go the geodesic type 1, and this will be the phi bar of S, and this will be mapped to phi bar, which is again like before, and we draw the alpha composed with the vector field, and so this is in the space of mathematics. It's a neighborhood of phi, if y phi is taken explored. So entry is a submatrix of M. And as you see, if phi is the identity, then we get the previous chart. Now we pass to nonlinear Grassmannians. So it is the space of all submanifolds. So we the space of all submanifolds N of type S. This means that it comes from an embedding of S in M by factorizing out the right action, the parameterization. So here we have this free action of if S on M. So it's a right action. Just, I will notify the embedding by G the diffeomorphism. So it's just, and so factoring out the reparametrization, we get the nonlinear Grassmannian, and we want to put a Francesco manifold structure on it. The infinitesimal action with infinitesimal action of the algebra of difference, which is the algebra of vector fields on S, is I will denote Zm, the generator by the vector field Z. So this is simply, and phi is the derivative of phi composed with Z. And now that we know that how the exponential looks like in the diffeomorphism group, we can write what is the flow of the infinitesimal generator. It's just composing with the exponential, so it is with the flow phi goes into phi composed with xpz, which is flow tz. We will not use it, but remarking this. So we want to do, we will denote by pi the canonical projection. From M to group, and we want to show two things, that the Cornelia Grassmannian is a Frechet manifold, and pi is a principal diffs bundle. So actually, we need the picture here, because this deformed heart is for the manifold structure. So oh.
Are we assuming always that S is compact?
Yes, it's a closed, compact without a boundary. There are versions of non-compact S, and it's even a version for compact with boundary. Even in a paper with Francois, we needed it for some free boundary fluid dual pair, and then we needed a case with boundary, and we found it on these problems. But I wanted to keep it simple. So, but for the length of a chart, so the first step, we want chart for the nonlinear Grassmannian. They call it also nonlinear show variety. It's really the nonlinear version of the Grassmannian of linear subspaces in the vector space, centered this pi really enters in the construction of the chart. So we need a tubular neighborhood of n and m. So we take the normal bundle. It will be modeled on the sections of the normal bundle, but we don't take the abstract normal bundle. We take it with respect to Riemann metric. And then, so with this normal bundle to n with respect to a chosen Riemann metric, we build a tubular neighborhood of M. I guess here we either write X or we write, but then we have to restrict to sub to small vectors. But if we use alpha, yes, we don't have to do this. And we remember the projections on n. So this I denote PV. It's defined only on the tubular neighborhood of m. So here n is the red heart, and here is the tubular neighborhood. So this one, spoil the picture. So this is V, what are we doing? First, make it more clear. Okay. First we let's define first what a normal embedding is. Normal embedding. This is the name we use with François in our paper. Normal embedding with respect to phi and with respect actually to tubular neighborhood is an embedding that comes from a normal vector field. So here when y is a normal one. So it is a normal embedding is one that we gain with the normal vector field. So y5 is a section of the normal bundle. So please excuse the identification of n with s. This is done by the embedding phi. So y5 is actually a section of phi star Tm, but identifying this with n is a section of the normal bundle. So these are the normal embeddings, and we use them to, you see, they are constructed with the space which we need. So the next step is to identify normal embeddings with submanifolds. So they are in one-to-one correspondence with their image. Which are so this will be the chart neighborhood of n, which is built by those submanifolds that project diffeomorphically onto n by this PV. Such that PV from n bar to n is a diffeomorphism. And then here we have this correspondence. So in the end, we have correspondence between elements in the submanifolds in the n and normal vector fields on n. If we look in the picture, so maybe I put what should I write here? It's the phi of s, and then we have the normal fiber x and orthogonal with respect to the metric, and then we apply this alpha, which is basically the exponential map, which will give us an we apply it to a vector. I forgot the vector. So this is y of x. S1 doesn't matter since we make this identification, and then we go along the geodesic time 1, and then we're like here. And this is phi bar of s. And as you see, the projection is along this fiber of the tubular neighborhood on two axes. This is P. I don't know if I will, but I hope the picture is more clear than my explanation. So in this way we get the chart. Of course, there is a lot of work to show that the chart, the changes are smooth, but you can look in the book of Convenient Setting of Global Analysis, or even better in the book of Peter that appeared at Shiva Publishing House in the 80s. So there is still work to do. But in this way, we also get for free a small section of the projection of pi. We have this here. We have this three action. In finite dimensions, if the action is also proper, then we have a principal bundle, but here it doesn't work. But if we show that we have local sections of pi, then this implies that we get the principal bundle. And the local section is so here down is the Grassmannian. So we want to each locally around n in Dn to n bar we will assign the normal embedding. So this will be S of or sigma of n bar, the local section sigma. So we have a section and the action is free. So we get the principal diff S. So this was part 2. And now we want to get them as homogeneous spaces of diff M, like for the linear Grassmannian. Similar things you will see work for the space of nonlinear flags. So section 3 is the diff M. Remember, so for the usual Grassmannian, if we take the linear Grassmannian of n-dimensional linear subspaces of Rm, we can write it as manifold of linear embeddings, linear injective maps from Rn to Rm, factorized by GLM. This is embeddings modulo diff S, but it is also GLN. Oh, sorry, here is GLN. We also have the transitive action of GLM, the big M, factorized by the isotropy subgroup of Rn in Rm, which is so the stabilizer, which consists of matrices star, star, 0, star. It's a stabilizer of Rn in Rn. We get something similar for the Grassmannian, but we will not obtain the whole Grassmannian, but a union of connected components. So the GLM action is, in this case, the diffm action, which I the title. So elements diffm we will denote by F, those in diffs by G. So F acts from the left on submanifold, simply by in the image of N by F, and the infinitesimal generator will be just X ring phi. Oh, no, here we are on N. So on N, then what we have to do is to restrict X to N and to take the orthogonal projection. This is the section of the N orthogonal. So we have this action. We have the stabilizer subgroup of N. Consists of those diffeomorphisms of N such that N is preserved as a set. And we can see it is splitting Lie subgroup of M. We just need a chart. We had the chart for diffm constructed with the local addition alpha, which was the exponential map. But now we will use an alpha which is compatible with N to N, adapted to N. So chart. So the submanifold, the speaking submanifold chart is constructed with alpha, local addition alpha, such that alpha is with alpha such that a vector is tangent to N if and only if this map P alpha, which was a diffeomorphism onto the neighborhood of the diagonal, is in N cross N. First is clearly in N, but we also have it's if and only. So then the previous chart we had is a submanifold chart, and we can show that it has this action has local smooth sections. For the diffm option. This means that the section will be this time, maybe it's not clever to use it the same sigma, let's use S. On the neighborhood of N, it will be the same one we had before, to the group, which in our case is diffm. So it's just obvious thing we can get with the normal embedding. It's just so what does it mean local smooth section for the action is that S on applied to any n bar in the neighborhood, acting on n gains the n bar we started with. And here n is, which is phi of s, is again fixed, like we had this was. To write S, we need a smooth extension map, because we will have this normal embedding phi bar, which gives us a vector field along the embedding, but we want the vector field on the whole manifold M, not just along the embedding. So it is constructed using a smooth extension map, using a smooth extension map. So it takes vector fields along phi on M, and vector fields on the whole manifold M. So it's just extending y phi to y theta, and a vector field on the whole manifold M. And now we can build our S. We start S of n bar. So we have first to sorry. I will better write it as a chain of. So we have n bar. From n bar, we know how to get the normal embedding phi bar, which in her chart is written with the help with a local addition and a vector field, a normal vector field to N, which, as I told you, identifying N and S can be seen as a vector field along phi. And now to y phi we apply the extension map, so we have this y tilde. So we just take y ring y tilde, which is the diffeomorphism of M. You recognize here the chart we have for the diffeomorphism. And one can easily check this section of the mutation. So this was from the fact that it has local smooth sections. This is a general theory that we get that the action is locally and infinitesimally transitive. We will need this for our quadrant orbit. And we also get that all the orbits are open and closed. And now I told you that we will not, the homogeneous space is not the whole nonlinear Grassmannian, it's just the different orbit of an N, which we denote by with an N here on the left. And now we know it is a union of
Cornelia.
Connected components of.
Cornelia, can you hear me? Sorry to interrupt you. Can you write a little bit larger?
Yes.
It's getting a little difficult to read. Thank you.
I will erase the thing. I start again. Union of connected components of group S. So the idea is that we don't get the whole Grassmannian, but just the union of connected components, but which is well enough, good enough. With the conjoint orbits, the Hamiltonian group is connected. We've seen in the first lecture, very first lecture, how it's constructed with those Hamiltonian isotopies connected to the identity. So anyway, the conjoint orbits will be connected. So we will always have to take connected components of the Grassmannian to get the conjoint orbits. How much time do I have? Where is Joanna? How much time?
I remember 10:55.
Okay, so I only have 2 more pages. No, 1.5. Because just the decorated Grassmannian, and then the next, everything else will be left to the second lecture, and then Stefan will take lectures 3 and 4. So, okay, now I will write it down. So now we will put decorations on the Grassmannian. There is an older paper of Alan Weinstein. He's constructing he has weighted Lagrangian, the Grassmannian of weighted Lagrangian subspaces as a conjoint orbit of the Hamiltonian group. So there the decoration is a weight. So, but if you want to get oriented Grassmannian, so if you want to integrate forms, not densities, but forms, then you need an orientation, and so this is also kind of a decoration. So our last section today is decorated. I don't write Grassmannians. All our Grassmannians are non-linear decorated Grassmannians. So what are possible decorations? They have to be natural. So we had it in one of the talks on this nature. Units. It is natural, or what is constructed with a tangent bundle and so on. So, but we have also more. So kind of functorial on S, they should depend. So we can take simply S, or we can take functions of N on S, or more general differential forms on S, closed differential forms. We can take also, this is or we can take orientations, so section of the orientation bundle, or we can take densities. So which are so S here is k-dimensional, or we can take positive densities. If we want the positive non-zero densities, or even what we call these differential characters on S. So let's take the simplest case. Here we will get the tautological bundle over the Grassmannians. This I learned from Mahmoud. It is maybe I write here. So decorations, if we denote it by f of s, so we will take associated. So if s acts f of s is any of this, and then we take the associated bundle for the diff s action. So it's a bundle over ms modulo diff s, which is nobody else but the numerical Grassmannian. So this associated bundle is the bundle of, so this will be decorated Grassmannians with objects of type F, and this will be the forgetful map. So we forget the decoration, and we are just left with some manifold. I go back to the tautological bundle. So it is here. So maybe this associated bundle. Now, Joel will say that he cannot see, and so I that we will see. You will see all the examples. So the tautological bundle is the associated bundle for the diff s action of s. So it is here the projection, the forgetful map over GRU SM. I missed this one step, sorry. Just to explain why it is called the forgetful map. To a class phi and f, it's not good, lambda, in the associated bundle, we associate phi of s, and then we transport the decoration lambda from s to n. So we get here the pair n, and then some lambda n decoration on n. In the case of the tautological bundle, these are pairs n, and here we have only points. So there are n and x, such that n is in GR, I don't write it anymore, and x is in n. So you recognize the, it's like a tautological bundle over the Grassmannian. And we can take here the projection Q on the on M. It's on the second component. And now the tautological bundle can be used to transport to do transgression of differential forms. So if we start with alpha, a k plus L form on M. Yes, thank you. Omega in k plus L. Then we do pullback by Q. So we are on this on the tautological bundle, which is a bundle with fiber S. So we will do fiber integration, And the result is an L form on the nonlinear Grassmannian. Here one has to be careful with the orientations. One can take here the oriented, so to have an orientation on n, so in order to be able to fiber integrate and so, but everything works. And so this is the transgression. And the KKS symplectic forms on the Grassmannian are of this type, obtained by transgression. And I only want to decorate with the density. If I have 2 minutes, yes. Because Stefan will also talk about decorated flags, and then he will make things more precise. So to save time, I will write it here. So this is weighted. Yeah, S weighted on M. So this is the as before, the associated bundle with densities. If one can take volume forms, and so this is the weighted Grassmann, and it can be identified with the space of some manifolds endowed with the weight, with the density on N. And you have again a forgetful map, and we wanted to be the base of a principal bundle. So if we fix also a weight on S, then we can factorize by the group of S mu, volume preserving diffeomorphism of S. But in this case, we don't get the whole weighted Grassmannian, but just those that are obtained from S, from S mu, and we can characterize them when S is connected. So one can write it also as an associated bundle, but with the instead of the whole density space, we will take the so it's M cross the orbit of mu, and this is the space we need, because here there is the transitive action of the diffeomorphism group, and this orbit of mu, if S is connected, then the orbit of mu by Moser trick is exactly those densities such that the integral it has the same total mass, but if S is not connected, then I think this will explain Stefan in more details. So these are the spaces we will work in the next 3 lectures. And thank you very much for your attention.
Thank you, Cornelia, for this wonderful talk. Any questions from the audience? Any questions from the online audience?
Yes, I think. Did somebody raise their hand? No, never mind. But feel free to raise your hand if you have a question, or just unmute yourself since there's not a rush of people.
Yeah, just
Okay. Sorry.
Can you have the question
Can you hear me?
online?
yeah. Can you hear me?
Yes.
Just a comment. There should be positive densities in the end, because
So-
the Mozart trick would not work otherwise.
Okay.
This will never end. Can you hear me? Okay. So I guess I have 2 questions. The first one is rather general. So just to, since I really like the kind of panoramic view you were giving, I would like to understand. At some point you mentioned the convenience setting. Do you know the? But
Everything is Fréchet, so one can use also other.
I mean, it's an exchange.
Yes,
You
but
really
the
know
convenient one is convenient.
in all the examples you mentioned.
Yes, it's Fréchet.
Okay.
Go to locally convex spaces.
Okay, so you can use this Michel Bastiani calculus.
Yes,
So
you
the
can
same.
use anyone, any calculus, I guess, because on Fréchet, usually, Stefan, am I right? On Fréchet, they coincide on this calculi. I think so, most of them.
Most. Oh, okay. And the second question is a bit more precise. So perhaps you can point me in the right direction, because I wouldn't expect to have a full detail. But at the very beginning of your talk, you commented about the how to give the group of diffeomorphisms this manifold structure in a natural way, you know. And just for sake of simplification, say that M is closed, right?
Yes.
So for some time has been bugging me this argument that I find a bit obscure in Omori's book, because you said the other charts are, I mean, built by translation.
Yes.
But I guess you will prove that this is a group by using the local Lie group theorem, right? Where you just have to show that the operations are smooth in a neighborhood of the identity, and then
I would just compute the chart change.
yes, but you have to prove that the inverse is smooth and the product is smooth, right?
The change is smooth from vector fields on M to vector fields on M.
That shows that it's the manifold, and now you have to prove that it's a Lie group. So
True. Yes, but there is yes, there are this how to say specificity that you lose the left composition, left translation, you lose the degree of differentiability, and then you have to so it's they're not say really so I can point to you the books where you can read.
okay, but I guess we were working in a set of smooth functions, so you really don't lose.
Yeah, maybe I can comment here a little bit. To prove smoothness of composition in the Bastiani calculus is horrible.
Oh, thank you.
So the first proofs by Joshua Leslie in his dissertation with Henri Cardin was wrong in his publication. So Gutknecht was the first one who in his doctoral dissertation gave a correct proof. And when I did write this proof in my book in 1980, I was horrified how complicated it is. And I thought there must be something wrong in the setup. But if you pass over to convenient calculus,
Well, yes.
then you just have to check that composition maps smooth curves to smooth curves.
Oh,
And the smooth curve of a diffeomorphism is just a smooth mapping from M cross R to M, which happens to be a diffeomorphism. And the second diffeomorphism is of the same thing. And so it is just a finite dimensional chain rule that you have to apply. And this horrible proof, tens of pages, if you look in my blue book, it's just condensed to 3 lines.
yes, I know.
So
I get that proof, but I get
for the inversion, it's the same. So for the inversion, it's just a finite dimensional implicit function theorem that you have to apply, and you see that then inversion of the diffeomorphism group is smooth. And I think this is the main reason why convenient calculus is easier to apply than Bastiani and so on.
So it would be fair to say that nobody took the trouble to write a clear proof of the smoothness, say, of the inverse in the Michel Bastiani setting.
I think I did in this blue book 1980, but if you look there, it is horribly complicated.
Well, I will deal with horrible if it's written. So maybe then I can ask for the concrete reference. Thank you.
Okay, I think someone was trying to say something from the online audience, or not?
I suppose not.
Any more questions here or wherever you are? Because if not, then we will thank you later again.